We've got a video here about solving trigonometric equations, and it builds on work you would have studied in year 11 and perhaps 10, but we're extending on it and showing some examples. So this video will be quite substantial with examples to hopefully support your learning. So let's go back to a few things. We're going to go back to the difference between an equation and an identity. And an equation is a statement of equality. But so is an identity. It's a statement of equality. So something equals something. The equation is only satisfied for particular values of the variable. So particular values of the variable satisfy the equation. It might only be one, or it might be a series of them, but it's not just any old value. An identity is true for two expressions or more. So it's equating two expressions, and it happens to be satisfied for all values of the variable. So for all values of the variable. So you've seen examples like sine x on cos x equals tan x. That's an example of an identity. The Pythagorean identity, which we looked at recently, the difference of two squares, difference of two cubes, there's many. Now, focusing on trig at the moment, when we're solving trig equations, it's not always a case where we can just use a calculator, because calculators give solutions in a restricted domain, and this is called the principal domain. And it's the full term is the principal domain for the solution of a trig equation, and of course it depends on the ratio used. If it's sine, you'll have between negative 90 and 90 degrees, or correspondingly negative pi on 2 and positive pi on 2 inclusive. So the calculator will express it in that restricted domain. For cos, it's between 0 and 180, or 0 to pi inclusive. And tan, notice it's exclusive because of the asymptotes, the undefined aspect of tan, negative 90 and 90. So virtually the same are sine and tan, except for the exclusion / inclusion. Cos is different, it's 0 to 180 or 0 to pi radians. That's called the principal domain. The thing is with trig equations is that we have potentially infinite number of solutions, because if we look at something like cos, it just keeps going. So it's true too here, just without a definite restriction on the domain. There are infinite number of solutions, because every time we have our x-intercept, we have a solution corresponding. And calculators typically don't give those values. So we need to understand by hand methods. Looking at an example here, cos of x equals 1 on root 2. So we have to solve that for x. So what is the value of x? So it's the angle or the real number that, or numbers that corresponds to the solutions for x. And of course there's no domain restriction there. So we will have an infinite number of solutions, and we also need to work out how do we write that infinite number of solutions, because you'll be there forever. Okay, so in the first quadrant, let's see what's happening here. So we could do a little sketch of a unit circle, and we notice that the value there is positive for cosine. So we are in positive values, we are in quadrant 1 and quadrant 4. We note that the cos in the first quadrant, cos of pi on 4 We're going to work in radians, by the way, with this. You would say 45 degrees, wouldn't you? Cos of pi on 4 is 1 on root 2. So we have that there, the pi on 4 angle there. But it is also true that we have in the fourth quadrant the acute angle pi on 4 works there. Now the acute angle is pi on 4. That would make the solution pi on 4, which corresponds to that one, or that angle there, that the acute angle is pi on 4, but if you go counterclockwise around till you get there the correct way, you'll have 2 pi take pi on 4, which is 8 pi on 4 take 1 pi on 4, which is 7 pi on 4. But of course there are infinite solutions, so going from starting again at 0, again we can see we can go in the negative direction as well, which would be clockwise. We could go more than one revolution around anti-clockwise. So we're going to have solutions larger and smaller than both of those. We're going to have negative and positive solutions. How do we write all this? We're going to have, for example, based on the pi on 4, we're going to have pi on 4, and if we go clockwise there'll be another solution which is called coterminal. And that's the same solution, but it's a certain number of rotations, and the radius of the unit circle ends up in the same position, but it's been around more than one revolution. So that would be, for the first one, pi on 4 plus 2 pi. Now remember, if you're in degrees, that'd be 45 plus 360 if you're in degrees. So that will happen again at 4 pi, and again at 6 pi, because you're adding one revolution, we're adding 2 pi on every time. Same with 7 pi on 4 plus 2 pi plus 4 pi plus 6 pi. And on it goes. But also it happens, if we look back at the pi on 4, it'll happen the other way around, as we said a moment ago. So we have all these plus or minus. Same with the 7 pi on 4, plus or minus. Let's look at the pattern for the solutions for x. So let's tidy all this up, because we've got to solve for x. Solutions are x plus or minus not just 2 pi, but multiples of 2 pi, as we saw. Same with 7 pi on 4. So let's let n equal an integer. That's what the capital boldface Z means. And we could say it's 2 pi n. Sometimes you might see that as things like 2n pi means the same thing. You might even see other letters like k used sometimes. They're integers. It means that any integer value. So that's 2 pi times n, and the same with 7 pi on 4. That's one way of writing the solutions. So x equals pi on 4 plus or minus 2 pi n. X equals 7 pi on 4 plus or minus 2 pi n. Or, if you're crafty, you'll look at the symmetry here. You'll come back here and look at the symmetry. And this is another option for writing the answer. You don't have to write it both ways, but you could say that we've got 2n pi, or 2 pi n, plus or minus pi on 4. You can see that from the diagram there. That's the same way, and you can write all solutions covered that like that. So it doesn't matter, you don't have to write it both ways, but that will cover all possible scenarios.